All right, let's keep pressing forward. The statement now reads, a uniform charged rod length L, charge density lambda, slides out the x-axis at a constant speed v. At time t equals 0, the back end passes the origin, so its position as a function of time is x equal vt, while the front end is at x equal vt plus L. Find the retarded scalar potential at the origin as a function of time for t greater than 0. Is your answer consistent with the LW potential and the point charge limit for L less than Vt and lambda L equal Q? Do not assume that V is much less than C. Okay, well, I think we just have a case of geometry that we need to tackle now. So the retarded time and position for the back end, well, that's V minus WT1 equals C T minus T1. So if we know that it's at the origin for the back end at this particular time, then now we can move on through. We get V T1 and C T minus C T1. So now we just have to distribute and solve for T1, which we do there algebraically. We cancel some C's, and only to get to V over C plus 1. Just, we keep our notation consistent. That V over C means a lot. So here we see that T1 is equal to T over 1 plus V over C. Similarly, we see that the retarded position X1 is equal to V T1, so that's Vt over 1 plus V over C. Similarly, the time and end position for the front end, C times C times T minus T2 is equal to V2 plus L. And so if we solve this for the T2, we push the L to the other side, factor out T2, and we see that T2 is equal to CT minus L over V over C. Factoring out a C for both of them to allow us to cancel gives us T2 is equal to T minus L over C and 1 plus V over C. So X2 minus Vt, X2, the retarded position, is equal to Vt2 plus L. And if that's the case, what we see here is that for the retarded time, we have to distribute everything with that darn numerator and denominator. And you see I just kind of fast-forwarded that process. And you see we get cancellations of V's and L accordingly. That's actually kind of surprising, but I like it. But yeah, whenever you find the common denominator with the two, you see that that's where it comes from. Nonetheless, we see that the retarded position is Vt plus L over 1 plus V over C. Isn't it kind of weird how these symmetry, or maybe not symmetry is not the right word, but these forms keep popping up? I promise you they're going to come back again. So at, the origin, V of 0 of t is equal to 1 over 4 pi epsilon naught. And again, we're evaluating this between the retarded position 1 and retarded position 2. So x1, x2 of lambda over x dx. Easy enough. That's just natural log. Lambda is a constant. Push it through. We see natural log of x2 over x1 due to the rule of logs and the minus. So if we plug them in, what we get here is that the retarded positions have denominators that cancel. We love that. And so we're left with lambda over 4 pi epsilon naught ln of Vt plus L over Vt. So if in the point charge limit, if L is equal to, or if L is much less than Vt, if we factor out a Vt for everything, then our numerator and denominator cancel, and we're left with lambda of 4 pi epsilon naught ln of 1 plus L over Vt. Clearly, we just said that L was much less than Vt, so if we hit that expansion, the natural log expansion, at least to the first level of, to the first order, we get that ln of 1 plus L over Vt is just equal to L over Vt. Again, that only works if we have epsilon sufficiently small, so ln of 1 plus epsilon is just epsilon. And here, epsilon is L over Vt. So with that being said, we push that L out, and we're left with lambda L over 4 pi epsilon naught 1 over VT. But what did we say was the point charge limit with respect to lambda? Well, Q was equal to lambda L. So indeed, we see that we have Q over 4 pi epsilon naught 1 over VT. Now, the question asked us to compare this to the LW potential. So let's see what's going on there. If that's the case, we factor C out from the LW scalar potential, cancel them in the numerator denominator, so that's where we get our Q. We see that here, script R minus script R vector dotted with the velocity over C is equal to VT plus V squared TR over C. And we see that with the TRs, we have to cancel a lot of things. And so we're left with a VT after the full cancellation. Okay, that's not terribly bad. So in a limit, L goes to 0, so TR is equal to T1 equal to 2, and hence V is equal to Q over 4 pi epsilon naught 1 over V squared, or VT. So yeah, actually this does work out quite nice.